interested in trying to study global CoT analysis. You can learn more about this by reading our introduction. But the kind of like TLDR here is something like many times or in the past we've basically seen that Mech Interp has studied a lot of like extremely low level properties of models, things like circuits or like single forward passes through like SAEs, probes, whatever, all of these various methods. And one possible failure of Mech Interp is to study higher level properties of models just in the same way that like many different fields of science are on a different level of abstraction. Um, and so the goal of this project was kind of to scope out and do a little bit more of that, where essentially what we do here is we take lots of different like rollouts, thousands of rollouts on the same prompt, and then like cluster various parts of the chain of thought to find patterns across different chains of thought and would hopefully find patterns across how models solve particular problems. And we introduced two methods for doing that, which we'll discuss in this talk: semantic step clustering and algorithm step clustering. One of which is a more fine-grained way to do this, and the other of which is a more coarse-grained way to do this. And both can give us sort of different insights into what quote unquote structures look like in chain of thought. Cool. So we'll get started.
Can people hear me? Hello.
Yeah.
Yes. Okay.
Yeah, we can hear you.
Wonderful. Yeah, I am Daria, as my username suggests. I will take the semantic clustering part. Riya, when I say next, you can switch the slide if that's fine. Cool. Okay. Yeah. So our first idea, or I guess there was an attempt at the start where we were clustering by activation similarity. In our setup, like this isn't covered here because that just produced really messy graphs. So the idea was to, like group all the things that have like similar enough or like high enough cosine similarity in their like last layer residual stream activations. um I think on the last sentence, maybe it was last token, we tried a couple of things. But yeah, then it was like unclear what to call those groups, because they're like similar. Yeah, like it's unclear what words to assign to them, because sometimes they would have like very different or yeah, like semantically they would correspond to very different steps. But anyway, that's a side quest that kind of failed at the start. Um, but this is a method we ended up settling in. It produces fine-grained and detailed graphs. And the idea is, so for the thing you see on the right, we just put it here because it's pretty. And it's, yeah, like very informative as it is. But the point is that so the green, or sorry, the start node is like the beginning of a rollout. The green node here is 0. That's like the one of the answers. And then, or I think the only answer in this case. Anyway, and then every path from start to 0. Here you can see like edges being directed. But every path from start to 0 is a different chain of thought on this prompt, in this case by GPT-OSS 20B. And so the numbers on the nodes are like the amount of segments of, or like textual chunks across all these like however many rollouts there are here, that have that like that like have that particular semantic flavor. So like all the fragments clustered into the same node, they like have the same meaning, but they say the same thing in slightly different ways. So that's like what we're building towards. Yeah, and I guess since the next part isn't really uh like covered in the post very much, but we'll talk a bit about like our process of getting to a somewhat clear picture, although still very messy. Next. Well, so the first thing we tried, and this is similar to what we ended up with, but different in a couple of key ways. So first, you to like get your data for your graph, you take one prompt, as Ria said, like one math problem, and you generate a bunch of rollouts on that. I think we ended up with like 500 per prompt. Um, and then you split these rollouts into chunks. You can think of these chunks as just sentences. So you just kind of separate into separate or yeah into sequential sentences for each rollout. The thing we ended up doing is a little more contrived, I guess, a little more nuanced. Basically, we split sentences by like some other punctuation with a pretty confusing decision tree that we sort of just handwrote uh, based on examples. But this is what we call chunking. As you can see here, long sentences are, in this case, pretty nicely split. Um, so that the like steps are more discrete or like the separate chunks. The picture on the right with pink text. So the once we have all our little fragments for these rollouts, we would merge chunks that are semantically similar. Um, the idea was just so you use a semantic embedding model to embed every chunk. Um, and this model it's made to put paraphrase sentences like the paraphrased versions of the same sentence close to each other in embedding space. um and so we tried to leverage that to capture this like semantic similarity across chunks, and then we did some refinement with language model judge. Oh, sorry. So yeah. So once you have your embeddings, the thing we did, we just had some threshold for merging, and for any two embeddings whose like cosine similarity was above this threshold, we just always merged. So this is equivalent if you imagine all your like chunks being sort of nodes on some graph. This is equivalent, and you draw an edge whenever your whenever two nodes, whenever the semantic similarity between two chunks between your nodes is above the threshold, then you draw an edge. Uh, this is equivalent to just merging um, weakly connected components. So anything that's like connected in any way on this graph would be grouped into one cluster. This is I'm emphasizing this part because this is what ended up messing up our method and what we ended up changing later. And then part B is refining with an LLM judge. So that's just like for pairs whose cosine similarity, or I guess now we have these like groups of chunks, and for groups in which the average cosine similarity across pairs of fragments in those two groups is like above some threshold, we would pass to 4.0 mini like some representative sentences from chunks from each cluster and ask whether we should merge those two things. Um, yeah, I hope. I don't know. I think the like details are not that interesting, but maybe it's worth having a little bit more of that here, given that uh, we sort of left them to the very end in our post, and like our process isn't really captured there. And then so the last step, once you have these clusters of semantically similar chunks, is embedding the graph. We're using GraphViz. The point of this library is that it like makes maximally nice graphs, so it places things that are closely connected, tightly connected, close to each other. So I mean, okay, we still got really messy ones, but one thing that this feature gave us is that this is actually pretty cool to see, and you can see it on this like graph in the corner here. So the interesting thing that we noticed is so the red part is all rollouts that are incorrect that lead to the incorrect answer are colored red, and the correct ones are colored green. And because the software we were using was sort of placing tightly connected uh, nodes closer together. Um, we think that's the reason. You can see this sort of separation between the green part and the red part. So there is like a clear area that is like much more correct and a clear area that is much more incorrect. Maybe indicating that correct steps are like uh, more correlated between each other, or because like switches, like you won't ever have a chain of thought switch from correct to incorrect. Um, but yeah, that's just a cool feature. Um, okay, next, I guess. So this is a thing we learned from our first attempt. So this is, I sort of already covered this before. Um, I said, we were using chunks, but before we started using chunks, we were just sort of trying to make small toy graphs using sentences as like distinct pieces. So the pieces we would be merging. And I think at the end, when we like reevaluated anything, this only had a marginal, or it only made a marginal change. It like did not really decrease performance by a significant amount. Or I'll talk about what I mean by performance later. But basically, this wasn't like a huge issue, at least by from the perspective of a proxy task. But when we tried sort of using sentences instead of smaller pieces, we saw in just by reading like the clusters that we ended up with, the nodes in our graph, um, we saw this annoying thing where you'd have long sentences that each contain sort of several semantic steps, like rollout 10 here. Um, they would like accumulate, or they would get clustered with a bunch, like the individual pieces, which is like maybe not the worst problem, but this can be a little annoying because you have like the last part here in light blue, so 5 hex digits at most 20 bits. That's just like the ending of this thing semantically, and that would get clustered with like the rollout 72 thing. Um, so yeah, so that's sort of some motivation for chunks. Next. And then so this is also mentioned by me at the very start. But yeah, clustering by activation similarity happened. Jenna and Riya, Jenna was also part of the like Neel Nanda training phase during which we did it. They did a project trying to do that. So using you sort of do the same thing, but you would cluster by activations um, instead of semantic. And yeah, your issue is just like clusters don't have clear labels. Yeah, because they are like more fine grained than meaning, I guess. You can have two things that say the same thing, but or sorry, you could have two chunks at different points of the chain of thought that say the same thing, but because the like reasoning trace before it is so different between those two, the activations are actually like not that similar. And so they won't be clustered together. So you'd end up with like a bunch of nodes that have like the same word label, but not the or yeah, like but they're different nodes. Issues like that would come up basically. Anyway, yeah, I guess next. So yeah, this was our original pipeline, which I already talked about. So let's go to the next slide. Um, so the thing I described earlier, where we were merging things by semantic similarity, whenever your two chunks were, or like whenever that thing was above a threshold, um, that's failed miserably on our proxy task. I will describe our proxy task later, but sort of on the right here, you see what was supposed to happen. Or sorry, the like gray line would be the ideal situation, right? We're like predicting something and we want our like predictions to match the like true values, and this was very much not the case. Um, and the issue with our original approach was that so I sort of I talked about this in more detail uh, um, in the semantic model clustering, but left it out in the language model refinement. But as I said, we were clustering sort of weakly connected components. So whenever the whenever the cosine similarity between two chunks was above some number, we would just merge those, regardless of like the surrounding situation. Um, yeah, and the same, we sort of did the same in the LLM judge case. Um, and so, yeah, thanks. And so the issue with this is that long chains would get merged into one cluster. And by a chain here, I mean a sequence of clusters such that, or sorry, a sequence this is terrible. We made this terminology and now I'm messing it up. Probably says something about the terminology. Anyway, uh, merging chunks that are like similar to each other resulted in these chains where every pair of adjacent chunks would be similar semantically, but like the beginning, like the start of the chain and the end of the chain would be super different. And so you can see it in this example where this is like the word ladder problem on the right, or like the puzzle, how you can like go from head to tail in just a few switches. In the same way, you can radically change the meaning of your sentence by like small perturbations. And so hex digit 6666, each six hex equals binary 0110 would get merged with. So first digit six has leading zero, but we don't count leading zeros, which are like completely different things. Like the second one is talking about leading zeros, and the first is like converting the first six to binary and saying what the original thing is. So yeah, this was annoying. This led to bad chunks. Bad clusters. This explained why our proxy task was failing in part. Uh, So we decided to instead merge approximately strongly connected components. So instead of merging things like whenever our threshold was high enough, or whenever the LLM said to merge in the second step, we decided to first sort of calculate all the similarities, and then you would use your the basic idea is like uh, or intuitively you'd want to merge groups of nodes that are not only connected weakly, but they have like quite a few edges between them. So they're not like the example up top here. It like it's like a little more connected. I don't know, maybe maybe this is a little better. But yeah, but the bottom thing is like basically a chain. So you'd want to get rid of that. Uh, and we did this in both steps via next, I guess, um, via two slightly convoluted methods from two graph algorithms. This is actually very fun to put together, but our advisor, our supervisor, thought this was maybe a little excessive. It did end up working pretty well, but I mean Neil here. So for sentence embeddings, we use agglomerative clustering. I will like briefly go through this, and if people have questions, you can ask later, I guess. This is not like a key feature of what we're trying to explain, or like the message, the thing we learned from global chain of thought
It's a quick thing.
investigations.
Feel free to put any questions in the chat, and I can also answer them in the chat too. So that
Oh
way we
yeah,
don't
thanks,
interrupt
Sarah.
you.
Cool. Um, okay, so uh, the similarity. I guess I'll just say what the idea here is. So you find a pair of you start with like each chunk in its own cluster. Um, this is just like semantically useful, I guess. And then you find a pair of clusters such that they're like as similar to each other as possible. And similarity here is just defined as um, the minimum cosine similarity between like a pair of chunks. Or sorry, between a chunk in the first cluster and a chunk in the second cluster. The idea of this is like the worst similarity between those two things, right? So this is like a threshold, and what you do is you'd find your pair of clusters that have this highest, this best worst similarity. If that thing is above a fixed threshold H, then you would merge your two clusters, and uh, then you would be back where you started at with like a bunch of clusters. And so you can just repeat this procedure until no clusters can be merged. So until for any pair you look at, their like worst similarity is below your threshold. And so what this results in is a bunch of clusters that have this property that within any cluster, any pair of chunks have similarity, semantic similarity at least H. But you cannot like group any pair uh, beyond that to like preserve that property. Cool. That is agglomerative clustering. And then so that's like how we get our first step with sentence embeddings done. And then the LLM refinement step with 4.0 Mini is like a little bit different because here we get binary labels for edges, or sorry, for like, should there be, should these two clusters be merged or not? This is like the LLM's judgment, yes or no. It's no longer like a number between 0 and 1. And for this, we were using the lead-in algorithm. It's like an optimization, graph optimization thing. But the point, the like thing it ends up with is a bunch of clusters such that the target density is like at least a certain number, at least a certain number gamma. And target density is just like if you imagine a graph or like a component, a subgraph, and you have a bunch of edges there, then your density is like the number of edges present over the total possible number of edges. So, sort of, this is a measure of how close this is to a fully connected graph. And so, um, I guess the way you would think about it here is like if you take a bunch, like where does the graph come from? Imagine our clusters from the previous stage being separate. So being separate nodes on this graph, and each like larger cluster is a node, and then you just connect any pair for which the LLM says, "Yay, merge them." Um, and then so you target this density gamma in this like higher level graph, basically. And you get these connected components in which the density is sufficient, and then all of those clusters would get merged. Um, so yeah, and then we tuned these parameters by hand for each of these, just like with an example problem. This was like a little gnarly. It's very possible that there's like a significantly simpler, dramatically simpler method for getting graphs of similar quality, or that would do as well on the proxy task we have later. But this is what we converge to. Uh, yeah, I guess yeah, we can continue. So just to recap, you get a bunch of rollouts, just generate on like this rollouts on the same prompt. You slice them up into these chunks by a decision tree. That's the first picture. Then the second picture to the right of that is the merging step. So you group similar chunks together, and then once you have this representation, you basically already have your graph. You embed it, and the edges are they connect nodes corresponding to adjacent sentences in a rollout. Um, well, maybe. Uh, oh yeah, I guess Maria, what do you think? Should we take questions at the end or at the end of the next section, or like uh,
Oh yeah, let's take if there's any
no?
questions now, we're happy to take them.
Okay, uh, no questions. Let's continue on then. So now I'll talk about our proxy task. Oh, did someone? No, that was Rhea. Okay. Our proxy task that I mentioned before, we call it predictive power. So this is how we verified that our graphs were like actually doing something meaningful. Nothing of what we said so far. I mean, yeah, it's like fun graph algorithms and all, and like maybe it results in pretty pictures. But the goal here is to capture something, some like important information or like something actually interesting. Some like find some common structures, common patterns in your rollouts. And so far, we were just like, okay, here's like all the stuff we did. Um, but like you have, this could just be terrible. Like, we don't really have a validation of our method. Um, and so the thing we use is predictive power. Next. So the question is, given a beginning of a model's chain of thought on a given problem, so it says like, okay, let me think about this problem. Like, here's what it is. It maybe restates the problem, gets into the weeds a little bit, like tries a couple of approaches, and then we cut it off, and we just take that beginning up to some point. We take this prefix, and we ask, can our tool or like can we in general predict the model's final answer distribution. So in this case, it's a math problem. And we experimented with problems where models sort of converged to two common answers, or like there was like one right answer and one super common wrong answer. Later on, we sort of cleared this up a little bit by giving models only two answer choices. Hopefully, if this like scales in the future, if we go further with this, we would look at questions with multiple answer choices to make the question the task a little harder. But here we just have two answers, and the question is like, can we predict how often the model will get the right answer versus the wrong answer given this beginning of a chain of thought? And the TLDR is that we achieved, so the method described above achieved across uh, our sample size of our test set of maybe like, what was it, 7 different problems, on average, a better performance than any of the other baselines we tried. And it like very slightly, marginally uh, improved on the performance of Gemini 3 Pro when given the context of a bunch of rollouts as well, which we think is like a pretty good thing to say for our graph. Although like all the predictions, everyone's predictions were like not that great. But I guess I'll come back to it later. But so now for the details here. So uh how do we get the Riya previous slide? Um so the way we get the ground truth distribution for like what the model is going to say, or yeah, like what the answer distribution will be, we just resample with that chain of thought 50 times. And below is the original question we tried. It's just like an Amy question. Is not super relevant right now, but this is the one we like hill climbed our methods against. Um, yeah, next. So we tried, just like a little behind the scenes, we tried a bunch of things before we converged on the um, method we're using now for for like predicting answer distributions with our graph. It's like not immediately obvious how we should do this. We still don't know if our approach is the best one. It performs reasonably well, but like it's not immediately obvious what to do if you have like a prefix and you have a graph, um, and you're trying to use this graph to predict where the prefix will end up. And you hope, like, hopefully uh, I guess you can think that like the chunks on of your prefix can be chunked in such a way that like all chunks are matched to nodes of the graph, but then it's like unclear what you do after. So I'm not going to go into these approaches, but yeah, it's like we went as far as using a GNN and training a GRU to predict the distribution. Um, the thing we ended up converging on is like came from the simple idea of, so like why not just look for rollouts that are like pretty similar to the one we currently selected based on just like the clusters. The rollouts that like start that match the prefix pretty well. Um, and then we'd like score rollouts based on that. And then we'd use those scores, like how similar each rollout is to our sentence, to figure out the distribution. So like, you can imagine that if there is a correct rollout or like a rollout that goes to the correct answer on our graph, and at some point it like goes through a very similar sequence of clusters as our prefix, this should indicate to us, like this should be a positive update to the distribution, right? Because there's a rollout that's correct that is similar to what the model is saying now. So that's the intuition. Yeah, the thing we ended up using is it's like a little bit technical, but is there maybe next, Ria? Uh, yeah, so you would as I said, match the prefix to like the pieces of the prefix to clusters on the graph. And then you would slide. So now you're like, you can think of instead of a prefix, you now have a sequence of clusters. Like the prefix is represented by a sequence of clusters. Um, and then the thing after that that you do is so you slide a window of um, the prefix's length, so as long as the prefix, over the clusters of any rollout, like any given rollout, and you do this for each rollout, and you look for the longest common cluster subsequence that matches between, yeah, so the longest common cluster subsequence between that window and your prefix. Um, you sort of look across all your windows, you find um, you find the best window score. So you find the window that matches best, and you use that as your rollout score. An important detail here is that uh, like the way you score a window is you would add not just one for every matching cluster, not the same amount, but sort of you would account for how deterministic this cluster is, and you would add more for clusters that are more deterministic. So for clusters that lie on like only incorrect rollouts, you would like weigh those more in your window scores than clusters that lie on a mix of rollouts. Um, the idea of that was to uh, account for cases where like super common clusters, like oftentimes models will say something general, like all the time models just like restate the question, and you don't want to just like overwhelm your score with those coincidences, right? So like things that are if a cluster like um, is like very commonly said by correct and incorrect solutions, you don't really want to like assign a high score to it. Um, yeah, and then the thing we ended up doing after that, so you like each rollout score is the top window score for that rollout. Then you would find the top 20 rollouts, and add the scores if the rollout answered like if the rollout got the correct answer, and divide by the sum over of scores over all your 20 rollouts. And so that would be like the predicted distribution. Yeah, I feel like I've already dwelled on this too much, but feel free to ask questions later. Um, next. And so here's like what our tool predicted for, just for an example, for that example first question. Here on the x-axis is the predicted percentage. So what our rollout, what our algorithm graph approach thought. And on the y-axis is the actual resampled percentage of correctness. And so this is like maybe not incredibly impressive. Like we still mess up a bunch of times, but there is clearly correlation. Like it's a 0.6, 0.58 correlation. You can sort of see like a bunch of points close to the to the goal here. It's still kind of a cloud. Next, and then this is the Gemini predictions for the same question. And so this graph was obtained by just asking Gemini once for the distribution and plotting it, I think. Um, So we would just give Gemini the rollout, or sorry, uh, we would give Gemini the prefix and all 500 rollouts that were used to make our graph. So technically, it had the same context, and it did some clever keyword searching and like looking for similar parts as well, and analyzing the rollouts. And it did not end up with particularly good correlations either. This is like slightly worse than us on this particular prompt. But one thing you can see here is Gemini tends to predict, like, there are just like things that are common for it to predict, like I don't know, is that like 35-ish% and 65-ish%, and then 50% are like, you can see those lines in the center. And then it also really frequently just says 0 or 100. So this was like it just, there are just like some numbers it likes, and also it tends to say the prefix is deterministic more than it is, as you can see by the like 0 and 100 things. Next. So this was our initial validation question before we like came up with a bunch more. I really love this one. um, the inspiration for it was pop-up bagels in Boston. Really great, really high recommend. Uh, but yeah, we had some of those bagels and then wrote this question. So the question is, you put a bagel flat on a table and you slice it in half with a vertical cut. So top down, right? Uh, how many holes are there in total in the two pieces that you will end up with? And we asked, so here we tested Claude 4.5 Sonnet, which, mind you, is supposed to be a smart model. Um, and, you know, if you cut a bagel in half like that, when it's lying flat, you get these like, two C shapes, and each does not really have a hole. So together they still don't have a hole. And Claude would say two, 32% of the time. Um, and the solution, like the way it usually came to this, is quite funny. So it thought that um, the bagel was a torus. So it's like uh, a torus is like a bagel, but it's hollow inside. And we think that like maybe Claude has been trained too much on solving math questions. So it's like, oh, bagel, torus, okay. And then you cut it, and so if you imagine cutting a torus, then you get these like two straw-like things, two curved straw shapes after you cut it. So then each has a hole in it. And then your number of holes is two. Anyways, next. So um
Oh, I can also continue from here. Um,
uh okay. Yeah, feel free to continue. I think we already did this, or like I already talked about
yeah.
this slide. I'm not sure why it's here. Um, but yeah,
Oh, this is
feel
just
free to go on.
cool. So, yes, Daria explained. Here we go. Our main method, which we'll justify a little bit more through some ablation studies later, but something that was important with this like pretty arbitrary proxy task of predictive power is to have some strong baselines, which Daria mentioned before. Um, the first idea is just like use the exact same method we were doing, the largest common subsequence method, but instead remove the clustering entirely. Figure out if the clustering is even useful. Um, yeah, so basically we do this. That's the intuition for this method. Uh, we do the same sort of like sliding window thing, and find the like maximum window score across all the possible windows when you slide it down your rollout, and then we compare this for just like splitting our rollout by chunks or by sentences. So we can test sentences, and then we also have this really strong baseline. We have like 5 other baselines that are in our blog post, but another important baseline is the super strong baseline where we just like uh, call Gemini 3 Pro 5 times, given this prefix, and then average those 5. So as Daria showed you with the previous plot, when we just do this once, we see a lot of like zeros, a lot of hundreds, a lot of 50s, some like middle numbers that Gemini seems to enjoy. But surprisingly, when we call 5 times and average the results, we do a lot better. So there's like Gemini clearly has some signal here. So here are the results for lots of baselines and our current method. Our current method is on the left over here, performed by slightly the best across like 6 different prompts that we ran. So we have like right over here, but one thing you might notice that there's a lot of variance in the prompts. And this actually gray line corresponds to just like a baseline that only predicts 50% for all of the prompts. So you can see that like some of our baselines in comparison to this very, very trivial baseline are really bad. Like over here, the sentence baseline and chunking baseline on average, where you don't use our graphs, perform worse than just predicting 50. A baseline where you ask Gemini but don't give it any context, so no previous rollouts, performs worse than that. A baseline where you give Gemini some context, like we're mentioning, 20 rollouts or 1,000 rollouts actually performs slightly worse, maybe context overload here, performs quite well. And then our method performs by slight the best on these particular set of prompts. So another way to kind of like study and compare the performance of our method, and like something important to note, is that different methods kind of cater to different determinism buckets. So what is this? Some prefixes you might imagine of a chain of thought are extremely deterministic. Like in the prefix, the model has basically already solved the question. It's going to like follow some particular like small set of steps to get to the end of the question. Other prefixes are super variable. We chose these prefixes randomly, basically by like randomly choosing some length of, from our 1,000 chain of thoughts, and fixing a prefix of that length. And so some prefixes just have like one or two sentences, and can basically go in many, many different directions, versus others are more deterministic. So one thing you might notice over here, so 0 to 10 is our super deterministic prefixes, and our current method performs, on the left is RMSE. So if you look at our previous plots here, just root mean squared error from between actual and predicted. Here, yeah, perfect. Okay. So if you look at the low determinism bucket, you see that our method and then like a Gemini baseline do quite well on this, versus something like the sentence and chunking and a similarity baseline basically is just like embed a rollout using a sentence transformer, and then compare its cosine similarity to the cosine similarity of every single existing rollout in our map, in our graph, and see which ones it's most similar to, and use the top 20 of these and then compute the score like Daria mentioned previously in the same way. So we see that these methods do a lot worse in the case where we have like low deterministic prefixes. This makes sense. They're probably just like much worse at finding rollouts that match. Versus with our graph, because you've clustered all these similar things, and now you're using this method to like actively find rollouts that have done similar things in the past. You are basically like more precisely able to figure out that these rollouts match this existing one. And Gemini's also pretty good at this. And if you read like Gemini's response particularly when making predictions, this somewhat makes sense. Like Gemini kind of like reasons through how the problem might go and which existing rollouts actually follow the particular method. So then in the middle, all of our methods are kind of like, more similar. And then in like high deterministic prefixes, here's where our methods do worse than like sentence or chunking baselines. And the idea here is like it's really good to just guess like 50 basically, or like guess like something like kind of in the middle. And our methods, on the other hand, somewhat like appear to quote unquote like overfit to like what the particular prefix looks like, and find some like small selection of like currently our top k value is just 20, so literally 20 rollouts that are similar. And for like very non-deterministic prefix, there's like actually way more than 20. So this could actually simply be resolved possibly by just like increasing the number of this. But currently as we have it, we do somewhat more poorly on these cases. Cool. And then our methods seem pretty complex. So how do we know it's actually maybe like a non like not super unreasonable? One thing we did is just ablated like lots of different pieces of our method. So our current method's over here. As Daria mentioned, we have the sort of thing where when we use our sliding window, we don't mandate a strict subsequence, just some sort of like common subsequence between our prefix and the like clusters in the window. So we ablate that. We require a strict subsequence. We also use all rollouts when computing our score, not just the top 20. We remove the sliding window. We use sentences instead of chunks, as we've mentioned before. We ignore the entropy label. So we just score a cluster using its position instead of also its entropy. And we also like don't use any weighting in the score computation. And all of these perform slightly worse, though you can see the first four especially are pretty similar. Did we try other embedding models? No, we didn't try other embedding models. We mainly use this one, or we did try it. We haven't run our whole pipeline through different embedding models. We mainly started, we ran our initial experiments with a variety of different embedding models and found this one to be the best. We didn't try OpenAI's. Yeah, the main intuition behind this embedding model is that it was particularly fine-tuned to on paraphrases, like Jared mentioned. And so that's like effectively what we were trying to do. We want paraphrases to be similar in embedding space. And so other models we found were like worse on paraphrase benchmarks and whatnot. Cool. Any questions before we go on to our next part, which is a totally different method we used? Cool. If we're all good, then let's go on to part 3. Okay. So far what we've kind of done is create these like messy graphs that, we kind of showed you earlier, where you like have the super fine-grained thing, where you have lots of like consecutive steps clustered together, and you have this like this messy graph from start to finish, where each path in the graph is a rollout, and each cluster represents like the same idea vaguely. But this is super messy, and it's hard to extract the clear quote-unquote structure or pattern across rollouts from this. One thing we naively initially expected is that these graphs might like have some nice shape that would tell us about what a problem, how a model solves a problem. But this didn't happen. Like our graphs are just like extremely messy and convoluted. You can even like see pictures of these from our blog post. They're just extremely messy, as depicted. So we tried to find a way to produce cleaner ones. And the idea here is really simple. Basically, we like are finding what we call algorithms. So given a new problem, we run like, or in our blog post, algorithm steps. I'll use algorithm steps for clarity. So given a new problem, we run like 300 rollouts, some large number of rollouts. We give a lot to GPT-5 or Gemini and ask it to identify key steps that models take continuously to solve these questions, as well as keywords that distinguish these steps. Then we use pretty simple keyword matching, which actually work better than multiple methods of LLM labeling. Because our CoTs do very similar things. So we literally just label sentences by which keywords they contain, with these disjoint sets of keywords corresponding to different algorithm steps. And then we are able to label rollouts this way, label clusters this way, whatnot. And so here's an example with a labeled rollout. So basically we passed, or here's an example using LLM labeling to label a rollout. Kind of a justification for why we ended up switching to just simple keyword labeling. So first, the idea was just like, let's pass a full CoT number by sentences and a list of different algorithm steps to an LLM and ask it to identify the like separation sentences between algorithms, like when does this rollout actually switch. Instead, we notice that a lot of rollouts actually switch like many times between algorithm steps. Like you get like 0, 1, 0, 1, where 0 and 1 are two different methods to solve this particular question. And models are surprisingly bad at labeling these. Here's an example where this fails. They kind of like are bad at switching back to the previous label. Versus keyword matching is really good at this. We just basically, so for this particular problem, just to provide some context on it, the question basically says we need to convert 6666 in hex to binary. And then there's like two ways you can kind of think about doing this, and count the number of digits. There's two ways you can think about doing this. One way is just like, there's 5 digits, each is 4 bits, 5 times 4 is 20, but 6 in binary is 0110, so we can subtract that leaving 0. And then that's 19 bits. So the other method is just like, turn this number into a decimal, and then figure out that 2 to the 18 and 2 to the 19 are between it. This also works. So one is, we call it algorithm step 1, and other algorithm step 0. So we can find like pretty obvious keywords that distinguish both methods. Like it's unlikely that the first method is going to like ever mention 419430, which is the decimal value of 6666. So things like this work. And then we could get like graphs like this. So basically, this is a super simple example that show us like how many times we switch between algorithm 0 and algorithm 1 in this particular question. And we find some rollouts, for instance, which we go into here, that actually, like this rollout just goes 0 to 1, this rollout goes 1 to 0, and this rollout goes 1 0 1 0 1. So models check their work a lot, is something we realized. And it's not too hard to label where they do this. So something we did initially, we don't talk about this in our blog post, but more behind the scenes, is we were kind of like pretty suspicious of our semantic clustering method. Do these clusters make any sense? Are they meaningful? One like small piece of validation that they're meaningful is that we'll have a small number of clusters that are different, labeled as having multiple different algorithms. So you might imagine if you have a cluster and you take every sentence in the cluster and you label it using this algorithm labeling process, where you just literally check every sentence for keywords. If you have clusters that have a lot of different algorithms in them, this is a sign that your clusters are like pretty bad, since we can't read all of the clusters. And so we do this, and we obviously find some mistakes, but for the large part, we don't see many mixed clusters. In the middle are mixed clusters. And most of our clusters subscribe to particular algorithms. Yeah, what are algorithm 1 and 0? So algorithm 1 is, these are both different methods to solve this hex question, where you need to like figure out the number of digits of 6666 in binary. And so algorithm 1 is basically, there's like 5 hex digits, each has 4 bits in binary. 5 times 4 is 20. But then 6 in binary is 0, 1, 1, 0, so we can subtract the leading 0 and we get 19. Versus algorithm 0 is just compute 2 to the 18 to the 19 and figure out the number in the middle. Or figure out that like the decimal value of 6666 is in the middle of those two. So 2 different ways to solve the question of how many digits are in this hex value binary. Cool. So more mixed clusters. There's some silly ones. But we looked at some of these. Usually there are like some bugs with keyword searching, which I'm surprised that there aren't more of these. Small word clusters. A third algorithms that are somewhat rare for this particular question. So one goal of algorithm clustering that I mentioned is just like to find the structure, quote unquote, find the pattern, reveal the like particular thing in common across lots of rollouts. We can kind of do this like pretty poorly using our semantic graphs too. Here's a semantic graph for the hex question, and you can see like when we cluster by algorithm 0, or like when we just like color by algorithm 0 versus algorithm 1, we do see like a separation in the graph. The intuition here is that like basically there's like some minimum path length optimization that our embedding package uses. And so since there's like not that many edges between algorithms, between roles that use different algorithms, we don't see like, we see them clustered pretty far apart. And so thus we can like maybe find a separation, but it's still pretty messy. Cool. So with algorithms, we can do, different algorithms used in the CoT reasoning, our algorithm 1 and 0. So with this like concept of algorithms, we can like do some other things. For instance, we can like reveal more structures and shapes and problems. So here's a question we artificially designed to kind of have what we expect to be like a tree structure. Basically, the question is you have like, you're debugging some bug, you have like 2 additional theories, A and B. And if you go down hypothesis A, then you would test C and D. If you go down hypothesis B, then you would test E and F. And so we expect this thing where a model that thinks about F doesn't immediately think about C, because these are 2 different leaf nodes on 2 different branches. Instead, we expect it to first go through B. And we do indeed see this. There's no edges between like F and D, F and C, E, D, E, C. We do see these back edges between like DB and FA, where the model like thinks about D and then jumps to the parent of the next branch. Tree structure. Also conversion structure. So here's like a question where there's like, the first part of the question is like 4 different possible methods. And the second part of the question is just a simple like plug in the arithmetic. And so we can see that models will basically use one of those 4 methods and then always use the only method for the second part of the question. And one thing you might note is that there's this back edge from method 1 to 4, which basically suggests that once the model solves the question after doing 4, often jumps back to method 1 to check its work, as opposed to jumping back to other methods to check its work. So there's things like this you can find. Something else you can see is different models solve problems differently. So GPT-OSS on this question, given a plus b equals 7, ab equals 10, find a cubed plus b cubed. has this like convergence structure where it uses 3 different algorithms and then finally a single one to like do the plugging in, versus Claude hops around between three different kind of like hops around a lot between the different algorithms and doesn't have this nice convergence structure. It also never uses this algorithm that GPT OSS uses a ton. So you can do some model diffing things. That's algorithm 3. Yes, we can pull it up. I believe I should have it here. Oh, algorithm 3. Oh, wait. This is just the like arithmetic required to finish the question. So once you figure out like your a and b values, then you just plug in like a cubed plus b cubed. So it's just like the final step to the question, which is why there's only one way to do it. Cool. Some other more structures we found that are kind of messy. Yep. So this is a summary of our algorithm clustering method. Basically, first thing we do is produce these algorithm steps and then like keywords associated with each of them, this sort of like step dictionary. And then we label rollouts by these particular steps. So which parts of the rollouts contain different algorithm steps. And then we produce these algorithm graphs, a simpler version of our semantic graphs. So whereas our semantic graphs compressed our rollouts by 35x and produced similar predictive power to Gemini, these compressed it a lot more. We haven't run predictive power on these though. So yeah, feel free to hop in with any questions at this point. We're basically done now. Last thing to talk about is future work. So one sort of intuition for future work, and we can talk a little bit about what we're also working on now, is that our two methods, algorithm step clustering and semantic step clustering, are kind of on opposite sides of this like supervision and then like coarseness axis. So the y-axis here is like how supervised the method is. By supervised, we mean semantic step clustering kind of like determines what things should be together in a very unsupervised way, where it just merges common things. Versus algorithm step clustering comes in with some prior that's been given to us by Gemini, or like GPT-5 or whatever, that these are particular algorithms that could be valuable and important. And then coarse and fine, this is a little bit more clear. Semantic step clustering is clearly doing a more fine job of clustering, versus algorithm step clustering is coarser and has like much larger clusters. And thus can show us, more high-level picture than semantic step clustering, while semantic step clustering is more faithful to the original rollouts. So we can imagine a lot of methods that are kind of in the middle over here as well. And that could be an exciting direction for future work. Cool. Yeah, that's all we have. Any questions?
Okay, I guess I can start. I do have a question. Well, maybe you already explained it or it doesn't make sense. But so in the prediction part, how better do the methods work than just taking the mean of the percentages for all of the rollouts?
Taking the average of the percentage for all of the rollouts.
Yeah.
So by this you mean something like for every single rollout, like or like to take the average of all of the like results for the rollouts. I see.
Yes.
Okay, so we haven't tried this baseline, but one thing you could imagine is it's pretty similar to this like 50% baseline here. So basically, like for most of our problems, or many of our problems, we have like basically around equal split of two different possible answers. Sometimes it's like 30-70. Sometimes it's like 40-60. Yeah, so some of these problems are like 50 or pretty close to 50-50, and so we do look around as well as this 50-50 baseline. We initially actually had that we haven't compared to the particular thing of just like let's try let's just use like whatever the initial value is. One thing you can imagine is this like works decently. I would imagine what would happen here is this works pretty decently for like the like low determinism prefixes. They're still pretty worse because some of them are like genuinely like pretty 50-50 since they're extremely vague. Versus because when you condition on the particular prefix, you get 50-50 even if the original distribution isn't. And then like the very deterministic prefixes just do like extremely badly. Because they like have some particular answer and we're just using the like prior and like what is the average.
Yeah, this
So
seems
it
like
could be
this
like a
seems
more
like a
extreme
nice
version.
baseline to try, I think. Or yeah, it's just like it seems strictly better than 50/50 because if you do have access to your collection of rollouts, then that's just like the priority you should have as the distribution. Thanks for pointing this out. I think we should like add that
Yeah.
baseline.
Um, Notes are bags with meant to go similar chunks, so the contents of a chunk is not taken into account. Takes in more context and temporality of chunks. So by temporality of chunks, you mean like where a chunk might be in the particular graph, or where a chunk might be in a particular rollout. Hmm. Yeah, so one idea here is like ideally we could find a principled way to do activation clustering that kind of that Daria talked a bit about. So, I mean, there's value to considering context. I mean, maybe like you do. Let's say a model says like, wait, let me rethink, and the start versus the end of a rollout. Those weights could be like have significantly different functions in the chain of thought. And so one way of like actively doing this in like a not super cursed way, since algorithm stuff or like activation clustering by itself is a little bit hard or a little bit cursed because like you get these graphs that don't really uh that Dart mentioned, like it's extremely hard to label like or it's hard to label what the exact like uh cluster should mean since you're providing all the previous context. You could get what you could do is you could take our existing semantic graphs. This is something we were thinking about doing, and then basically like within the graphs try to produce like more fine-grained like activation clustering differences. So we have some graph or some like cluster in our graph that says something like weight, and then we like cluster by activation within the weight cluster, and then we get these subclusters that like maybe are associated with temporality, like the location of the rollout and in the location of the chunk in the rollout. And that's one way to do this. You could also just try like raw activation clustering again, and see if you can like find like a less cursed, find like a more find like some reasonable way to interpret what the graph means. Yeah. Mm. Any final questions? Oh, we have some people.
Maybe just an idea that like
Yeah.
having thought about branching mid-trace as well, like for every token in the autoregressive steps. Many other tokens are also sampled, like creating a tree basically.
Yeah. Oh, so what is the idea here is to you said merge tokens?
No, like sample half of the solution in the chain of thought, and then like do a tree of like not branching only in the beginning and creating all these different traces that
Yeah.
are independent, but also like in the middle. Like for
Yep.
example, one algorithm is done and then doing different branches basically.
Yeah. One thing one could imagine to do, especially with the semantic graphs, is like take one of these semantic graphs, um, display like like one rollout or a couple rollouts, and then try to like do this resampling thing in the middle and see like how the like subgraph produced by resampling compares to like the like whole graph when you just like run more rollouts from the start. There's lots of work that has by lots of work we know like two papers that I know of that have done a sort of tested resampling as a method, like these like thought anchors and thought branches were done by past Neel Nanda scholars. And our method kind of was meant to be like a way of exploring more of this like global chain of thought graph than just by resampling. Since resampling only gives you like, you can imagine like one branch of this graph. But it would definitely be interesting to compare what the two graphs look like.
Yeah, I agree. One idea we had in the beginning but did not end up exploring is sort of how does the your sort of graph change as you like if you fix a particular rollout and then you go from like fixing a short prefix to fixing longer prefixes. You can imagine that like early on, if you just fix a couple sentences, then you get these like large clouds of things, and your rollout can go to many different places. And then the like more of the rollout you fix, the like smaller this cloud becomes. And so this is like maybe not the most relevant question, but I think it's kind of interesting to like understanding how deterministic chains of thought are. So like as you fix longer and longer parts of the prefix and resample from there, what happens? Like what's the how does sort of the spread of the graph you generate shrink with longer like prefixes, I guess.
Great, thank you.
Yeah,
Yeah,
this
it
was like
makes sense.
probably
It
very a
would
lot of
shrink.
custom models. Cool. Yeah, I think that's all. Thank you all for coming, and it was great to talk about our work.
Yeah, feel free to also reach out to us later if you have further questions. Our blog post is in the reading group channel.
Yeah, we've also published our code, all of our rollouts, and we have like a visualization tool where you can look at more of our semantic and algorithm graphs if you're interested. Yeah. Thank you all.
Thanks a lot.
Thanks.